Alrighty, guys. Decided to do one more video. I can tie it into section 2.4. However, it's sort of concerning limits at infinity, which is really going to be section 2.6 after we do some continuity. So kind of a preview, but it kind of piggybacks on that whole delta epsilon thing that we just visualized. Which is sort of a if you put a restriction on how close you want the outputs to go to a certain limit, then if I can find a certain little window of inputs that work, then that's what we mean when we say a limit exists. Okay. At some point when we were looking at some rational functions, I wrote something like this: the limit as x approaches infinity. Right? We've seen limits that equal infinity, but what about if the x values are approaching infinity? In other words, getting larger and larger and larger without bound, we might say. Without any kind of upper bound, you just keep on going. So as x approaches infinity, what happens, and how could we use precision to express those limits? All right. So let's think of this. Limit as x approaches infinity of that good old function 1 over x, all right? And in a previous video, I claimed that limit was 0. And I kind of talked my way through that. Again, that's not precise, right? Talking is just, I'm just saying we're going to get really small, and then the output gets really, or the input gets really big, the output gets really small. Well, how big do we have to get for a particular smallness of the function values? All right. Why is this true graphically? So if you graph this thing, at least in quadrant 1 for positive x values, the graph looks like this. All right, and it kind of swoops down and looks like it's getting close to this axis. And if you zoom to the right or slide to the right on your graph, on a computer, on your graphing calculator, you see that it's just getting closer and closer and closer, right? So it's shrinking, but it's not going to negative infinity. It's not shrinking in that sense. It's always going to be positive, because as x approaches infinity, that means x is becoming a larger and larger positive number. The answer is always going to be positive. So we have this string of positive numbers that's shrinking down. And so I claim that the limit is 0. Never quite hits there, but what that means is I can get it as close to 0 as I want. Because you might have numbers that are always positive, right? There could be another function where the function values are always positive, but yet they're always shrinking, right? But maybe they're tapering off to that level. Right, so how do we know that these are getting closer and closer to 0, and they're not sort of tapering? They're not going to stop at like 1/100th and then kind of stay at that height, right? How do we know they're getting smaller and smaller? How can we claim that the number equals 0? The limit equals 0. So in the previous example with the deltas and epsilons, that was when we were approaching a certain value, and so and in that case the limit was a real number, and so we sort of made a little stripe around the limit and said that we found the corresponding little interval for the inputs to work. For this one, if x is getting really, really large, if our limit is this, we still want to start with an epsilon. So for each, or for any epsilon, small positive number, there exists, instead of choosing another small positive number, delta this time, I'm going to choose a really, really big number. I'm going to choose a big positive number because x is approaching infinity. So I'm going to say there exists some capital M, right? I've seen some books use a capital M, some books use a capital N. I'm kind of using a capital just to emphasize that it's a large number, greater than 0. All right. I don't know how accurate this notation is. The professor who taught me this, to emphasize that it's a really, really large number, used to draw this. It's kind of 2 greater than signs. So I never really saw anybody do that except him in this scenario. But just let's take that to mean a positive number, but like really, really big, right? Really, really big. So for each epsilon, small number, there exists some big number such that for all x greater than that big number, right? I kind of call it like the point of no return. Once we pass, that's a really massive number. Once we go past there, let me write it like this. This is the way the book does it. If that's true, such that if you pass it, so if you let x values get beyond that m, then the distance between your function values and what you're claiming is your limit is less than epsilon. And again, that's just sort of, that means those two values are close, right? That means their difference is less than this sort of arbitrarily small number. So that just, the concept there just means that these things are getting close. It's getting close to the limit. Okay. So here our function is 1 over x, all right? And we're claiming the limit is 0. So let's try to fill those things in. So that means the function values, so this would be your definition of a limit at infinity, the existence of a limit at infinity. So again, probably from section 2.6, let's write definition. So if you want to pause the video, kind of write that down right now. Might be helpful, all right? What I'm going to do now, though, is apply it to this particular problem. So let me use my purple marker here, so just for some emphasis. So the function f of x, we've got a specific function here. We're calling it 1 over x. All right, and the limit is 0. That's going to make these calculations, that's why this is a nice example. So we're saying that the limit, or the difference between 1 over x and 0, we need to be less than an epsilon. All right. What's going to make this stuff nice now, let me clean this up a little bit easier. So again, we're taking the general definition of this limit, but now sort of applying it to this specific scenario. We argued earlier, well, first of all, something minus 0 is just itself. So 1 over x minus 0, because the limit is 0, I can get rid of that and just write 1 over x. All right. Further now, since the x is approaching infinity, and x is going to be larger than this m, which is a positive number, let me go back to our single inequality there. Since m is a positive number and then x is bigger than that, x is positive. So 1 over x is positive, which means these absolute value bars are sort of redundant. So in this particular case, I can get rid of those. And so simply write that this is less than epsilon. Okay. So this is a nice example numerically because it's pretty straightforward. So again, the function is going down. I'm claiming it's the limit is 0. Remember, the concept here, or the important thing to note, is the function never actually equals 0. So that's what makes saying a limit is, that's why we need this precision, because if it never equals 0, how do I know, again, that it's getting that close, that that's the target, right? So I claim it is, though. So you tell me, you say, well, I don't believe you. I want you to get, let's let epsilon equal 1 over 100, right? That's a very small number. That's a positive number. It's pretty small, right? You say, in other words, you think it's getting to be, I think you're saying to me, this is me doing your voice. You, professor, think that this function's going to 0? Oh, yeah, so I dare you to make it within, to get to that height, or within that height from the axis, right? Get to a 100th, and maybe I'll believe that you're shrinking to 0. Okay, so I say, okay, so what m do I have to choose now? How far do we have to go out in this function, right? If I say let m be 8, right, does that work? Right, so you're allowed to choose whatever you want. You chose 1 over 100. You guys chose that. Am I allowed to just choose whatever m I want? No, that doesn't work, because if m is 8, then what about x is 9? Right? If m is 8, what about x being 9? Right? Because then it says for all x bigger than that number. But if I write this, is 1/9, right? Is 1 over 9 less than 100th? No. Right, that's not true, right? 100th is smaller. So you can pick whatever epsilon you want. I have to figure out an m that's suitable to choose, right? I can't just pick any number I want. Let's say I go way further down, probably further than we can see, but let's say I say let m be 500, right? Let m be 500. I claim if you go out to 500, if you graph this function, and you go out and find where x is 500, I claim you're beneath the value of 1/100th, right? And so let's see if that's true. Well, if m is 500, then let's consider x being 501, right? Even larger than that, right? And then, so is it true now that 1 over 501 is less than 1 over 100? Yes, that is true, right? 1/500th is, or 501th, 501st, whatever you want to call that, it's smaller, right? If you've got the same numerator, then the bigger denominator is actually the smaller number, right? So that works. So m would work, and there I proved it. I proved that I can go further enough. Is 500 overkill, right? Could I have chosen a small? We saw 8 was too small, right? 8 didn't work. 500 works, so you can play around. I could say let m be 101. Let m be 101. Will that work? Sure, because then if I go to the next, and I'm just choosing the next whole number, but anything larger than 101 will work because of the whole denominator issue I argued. Could, in this case, you actually let m be 100? Yeah, you could, because then we need x values that are greater than that m, right? So then suppose x could be the next value, 101. All right, and then it's true that 101 is 1 over 101 is less than 1 over 100. And for every other x value down the line to the right, basically, that's also true. Okay, so that's a very simple example. You can do other examples with, if you start squaring x, and you're trying to find this minimal m that works, let's say the 100, it gets a little bit more, you have to be a little bit more creative, try to solve some things and figure it out. But anyway, kind of a cool topic. Again, will become a little bit relevant in 2.6. Having an intuition about what the limit is equal to, that's really what we need for this class this semester. But if you want to go down the line, that's helpful. This stuff too, with limits at infinity, is particularly helpful in Calc 2. So when you take Calc 2, you will do something called sequences and series, infinite sequences and infinite series, and you're dealing with infinities a lot, and this idea will appear there. So there you go. Have fun with that. Yeah, and then next thing we're going to do is jump into continuity, spend probably lots of lectures on that. All right.